Hello again. Today we're going to be continuing our discussion of probability by talking about dependent events. So let's get started. If you remember independent events, if I wanted to know the probability that event A and event B both happen, if those events are independent, then I can simply multiply those two probabilities together. But if event B depends on what happened when event A was taking place, then I need to change my formula for the probability of A and B happening. So I'm going to use the notation B and then a bar and then A. And the way I pronounce that is B given A. So what that means is, what is the probability that B happens if I know that event A did happen? Okay, so that's what the probability of B given A is. It's the probability of B happening if I know that event A actually happened. All right, so my original formula changes a little bit. The probability that A and B happens is the probability that A happens multiplied by the probability that B happens given that A has happened. All right, so here's an example. This is the way that I tend to talk about what it means to be independent versus dependent. So let's say that I have a jar of marbles and let's say that two of them are red. Okay. If I choose marbles and I am finding out the probability of choosing a certain color of marble, and I can do that two ways. One way is with replacement, meaning that every time that I choose a marble, I put that marble back. And then I choose another marble. So what that means is the probability of a given color during the second time that I pull a marble out, that's not going to change depending on what happened the first time, because the probability has stayed the same with every drawing because the situation hasn't changed. There's always the same number of each type of marble in the jar. But if I don't put the marbles back, that's called without replacement. So the situation is going to change with every marble that I pull out of the jar. Now it's a completely different situation. The number of red marbles has changed. The number of marbles of other colors has changed. And so the probability of being successful changes. So the probability depends on what happened the first time. So here's a clearer example of what I'm talking about. Let's say that there's a jar with 3 red marbles and 2 blue marbles. And so if I pull a red marble out the first time, the probability of me being successful with that is 3 out of 5 because there were 3 red marbles and 5 marbles total. Then I put the marble back. The probability that I pull a red marble out the second time is still 3/5. Even if I were to pull a blue marble out the first time and consider that a failure and put it back, then the probability of me pulling a red marble out the second time is still 3 out of 5. So the probability of me being successful with the second drawing of a marble is independent of what happened the first time. All right. Now let's talk about without replacement. So now I'm not putting the marble back no matter what color it is. So the probability that I pull a red marble out the first time is still 3/5, but now it's gone. It's not being put back in the jar. So the probability of pulling a red marble the second time is 2 out of 4 because now there's only 2 red marbles and only 4 marbles. Okay. Let's say the situation for the first drawing changed and I pulled a blue marble instead for my first drawing. Well, now the probability of pulling a red marble the second time is 3 out of 4 because now there are still the original 3 red marbles and only 4 marbles. All right, so you'll notice that the probability of pulling a red marble on the second drawing has changed depending on what happened the first time. It's not the same probability both times. So I would call those events dependent. So what happens with the second drawing depends on what happened the first time. So I can organize all of this by drawing a tree diagram. And so the first 2 branches show the possible outcomes for the first marble. It can either be red or it can be blue. And then from the ends of those branches, I draw 2 more branches because there's 2 more possibilities for the second drawing. And I use my given notation there for each of those branches. So R bar R on that top branch means that the second marble is red given the first marble is red. B given R means that the second marble is blue given that the first marble is red. R given B means that the second marble is red given that the first marble is blue. So whatever is given comes after that bar. And so B given B means that the second marble is blue given that the first marble is blue. All right, so we find the probability of each possible event. So I start with the first branch. And since there were 5 marbles and 3 of them were red, then the probability that the first marble is red is 3/5. And the probability that the first marble is blue is 2/5. Now remember, I'm not putting that first marble back. So the probability that the second marble is red, given that the first one was red, is now 2 out of 4. And the probability that it's blue is 2 out of 4. Then I go to the second set of branches, and this is the set of branches where the first marble was blue. So if the second marble is red after the first marble was blue, that's a probability of 3/4, meaning that the probability that the second marble is also blue is going to be 1/4. All right. And then at the end of each series of branches, what I'm going to do is I'm going to figure out the final probability of each sequence of events. So if I follow that top set of branches, I've got a red marble followed by another red marble. And so that's going to be 3/5 times 2/4, which is 6 out of 20. Then the next one is going to be red followed by blue, which is 6 out of 20. Then blue followed by red, which is 6 out of 20. And then blue followed by blue, which is 2 out of 20. And you want to make sure when you add up all of those probabilities on the far right-hand side, you get a total probability of 1. All right, so here's another example. For environmental reasons, a man only drives his car to work 2 days a week. The other 3 days, he rides the train. When he drives his car, he has a 10% chance of being late. When he rides the train, he has a 20% chance of being late. So we're going to create a tree diagram to represent the probabilities of being late on any given day. Okay, so he drives his car 2 days out of the 5 days of the week, so that's a probability of 0.4, meaning that he rides the train with a probability of 0.6. Using the other information, I can figure out that the probability that he is late, given that he is driving his car, is 0.1. And that means that the probability that he is on time, given that he is driving his car, is 0.9. Then we go to the second set of branches, which means he is taking the train. So the probability that he is late, given that he takes the train, is 0.2, which means that the probability that he is on time, given that he takes the train, that is 0.8. And so now I figure out what's at the end of each set of branches by multiplying the probabilities along the path. So the probability that he is late and drives his car will be 0.04. The probability that he is on time and drives his car is 0.36. The probability that he is late and takes the train is 0.12. The probability that he is on time and takes the train is 0.48. And if you add all of those probabilities together, you do get 1. So I know that my tree diagram is accurate. So now I can ask some questions about this situation. What is the probability that he is late and rides the train? So I simply need to follow that path that talks about him riding the train and being late. So that's this path right here. The probability that he takes the train times the probability that he is late given he takes the train. So that's the 0.6 times the 0.2, and that is 0.12. Okay? And what is the probability that he is on time given that he drives his car? So again, I need to figure out the probability that he is on time given that he drove his car. So I have a 100% certainty that he drove his car because I was given that piece of information. I just want to know what is the probability that he is on time given that he drives his car. Well, that's just one of the branches, that 0.9 branch right there. And the last question I might ask is what is the probability that he arrives to work on time on any given day? So no matter whether he drives his car or whether he takes the train, what is the probability that he is on time? So basically what I need to do is follow any path that deals with him being on time. And there are 2 of those. So I have to follow the path where he takes his car and he's on time, and I have to follow the path where he takes the train and he's on time. Okay, so that's those two paths right there. So that's going to be the 0.4 times the 0.9, or the 0.36, plus the 0.6 times 0.8, which is 0.48. And I add those together and I get a probability of 0.84. So he is going to be on time for work 84% of the time. So that is just talking about dependent events. If you have any questions on this, please let me know, and I will see you tomorrow.